Welcome to Discontinuities in Functions. Functions can be either continuous or discontinuous. A continuous function is, loosely speaking, one that you can draw without lifting your pen or pencil from the paper. If a function is not continuous, it is called discontinuous, and there are a number of ways that this can happen. The first type of discontinuity is called a removable or point discontinuity because there is a missing point. It has been essentially removed. This function is simply not defined at x equals a. Here's another example of a removable discontinuity. The function is defined for all values of x, but when x equals 3, you have to lift your pen up to draw the point at 3, 4. So it's not the absence of a value for the function when x equals 3 that makes it discontinuous. It's that you have to pick up your pen to draw it. Another type of discontinuity is called a jump discontinuity. In this case, you have to pick up your pen or pencil to get from one part to the next, but then you keep drawing. Like the name suggests, the function jumps from one place to another. Here's another example of a jump discontinuity. Now, when vertical asymptotes exist, you get what's called an infinite discontinuity. Here's another example of an infinite discontinuity. When vertical asymptotes exist, that's when you have the infinite discontinuity. The slant asymptote is interesting, but it's not contributing to the discontinuity. For example, if x equals, let's say 6 here, there's a point on the function, or 7, here's another point. So the fact that there's a slant asymptote isn't what's causing the infinite discontinuity. It's this asymptote right here that does. Another thing that could happen is your graph can just sort of stop. It ends, and when that happens, like it does right here, you get what's called an endpoint, and we call those endpoint discontinuities. And sometimes you have a situation where at the same value, so whatever a is here, you've got two things going on. So we just call those mixed discontinuities. So what about a function like this? I've got f of x equals the sine of 1 over x. You can try graphing that on something like Desmos, and you're going to get a really unusual picture. And it's called an oscillating discontinuity because the function appears to be approaching two or more values simultaneously. This is what it looks like. So you can see that it appears to be approaching 1 up here and -1 down here, and it's alternating closer and closer and closer together, so it looks like it's approaching both of them at the same time. So that's an oscillating discontinuity. All right, so time to test yourself. What kind of discontinuities do we have at x equals 2? So take a look at this first one, A. What do you think? All right, if you said jump discontinuity, you're correct. How about B? Right, so that's an endpoint discontinuity because it just ends here. How about C? So the presence of that vertical asymptote is giving us an infinite discontinuity. And then finally this one here at D, that's a removable or point discontinuity. And remember, the fact that there is a point down here that is at x equals 2 is fine, but we've got that hole right here. All right, here's another one to try. How about these? When x equals -4, so that's here, what do we have? Well, we've got two things going on. We have a point discontinuity, or a removable discontinuity right here, but it's also an endpoint. So with two things going on, we call that mixed. How about here at -2? Well, there's just a hole there, so that's a removable discontinuity. What about when x equals 1? So here I'm jumping from here up to here, so that's a jump discontinuity. At 2, you see the asymptote right here, so that's going to be infinite. And then finally here at 4, the function just sort of ends there, so that's an endpoint. All right, one more of these. So when x equals -3, I'll just give you a second. So see if you can write down what it is at x equals -3, -1, 8.5, 11, and 14. And I'll be back in a second with the answers. Okay, so let's see. When x is -3, that's infinite. When x is at -1, there's a jump discontinuity. When x is 8.5, that's a removable discontinuity. And when x equals 11, we have a jump discontinuity. And then finally, when x equals 14, that's an endpoint. All right, so it's pretty easy to see discontinuities when you're actually looking at a graph. But what if you just have equations like we do in this situation? So I've got a rational function, and if I factor it, I can get a little more information. So this is going to be x plus 2, x plus 3 over x plus 2. And you can see here, those are going to cancel. Basically what we have here is a line, but x cannot equal to -2. So we have a discontinuity at x equals -2, and it's just going to appear as a hole. So that is a hole, which we call a removable discontinuity. All right, let's try another one. How about this one? So here you can see in the denominator, we would have an issue if x were 2, because we can't divide by 0. So we know x doesn't equal 2. But this function is a little bit different from the last one. Even though we can factor the numerator, we can't just cancel out those x minus 2's, because in the numerator it's in parentheses, but in the denominator we have an absolute value. So what does that do for us? Well, maybe trying to graph this one would be helpful. So I'm going to go, let's say 2, let's do 2, 3, 5, 6, so we can get a sense of what this looks like. All right, so if I put a 0 in for x, I get 0 squared minus 3 times 0, so that's all 0. I'm going to get 2 over the absolute value of -2, that's 1, so there's a point here. If I put a 1 in, I get 1 minus 3, so it's -2 plus 2 is 0. 0 over anything is going to be 0. What if I put -1 in? So -1 squared is 1, and then -3 times -1 is +3, so that's 4. 4 and 2 is 6. And then in the denominator, I'm going to get the absolute value of -3, which is 3, so 6 over 3, that's 2. And then you can see that, oops, I just drew that in the wrong place. I think you can see that what I've got going on right here is the beginnings of a line going that way. And the slope of that line appears to be -1. Let's start with 3. Notice I'm skipping the 2 because I don't know what to do with it right now. If I put a 3 in for x, 3 squared is 9. 9 minus 9 is 0. So I'm going to get 2 over 1, which is 2. So that's here. If I put a 4 in for x, I get 16 minus 12 is 4. 4 and 2 is 6. 6 divided by 2 is 3. So that's here. If I put a 5 in, 25 minus 15 is 10. 10 and 2 is 12. 12 divided by 3 is 4. So you can see here we also have a line where the slope appears to be, well, in this case, 1. But if I continued that to 2, notice I'd be right here. If I continue this one to 2, I'm down here. Which one exists? So, or does either exist? Well, they can't exist, right? Because x can't equal 2. So what I have here is a jump discontinuity. So, I'm doing fine along here, and then I get close to 2, and I have to jump down, and then I can go back up on the other side. So this is a jump discontinuity. All right, next one. How about this one? All right, well, I'm going to factor the denominator just in case that's helpful. Numerator and denominator have nothing in common, but I do see that x cannot equal 3 and x cannot equal -2. So those are discontinuities. What type do we have here? Well, those discontinuities would cause asymptotes, so we have 2 infinite discontinuities. One at x equals 3 and one at x equals -2. All right, what about this one? So the first thing I want to look at is this exponent right here. So notice the 2 in the denominator of that fractional exponent. That's telling us that we are going to take the square root of what we get when we cube x. Well, we can only take square roots of numbers that are either positive or 0. So there's a domain restriction here. This function is only defined when x is greater than or equal to 0. Now, if x is greater than or equal to 0, and therefore this function actually has values, are there any restrictions? Would we end up dividing by 0 somehow? Is there anything weird going on? And the answer is no. You could plug in anything you want for x as long as x is greater than or equal to 0. So there are no discontinuities. And this function is continuous across its entire domain. So you can see not all functions have discontinuities. Some of them can be continuous, even if you have to restrict them to only being continuous on their own domain. And that's it. So thanks for watching.